What if one of the most consequential weapons in a modern great power conflict cost less than a used motorcycle? That's not a hypothetical. It's what happened in Ukraine, where small quadcopters, the kind of machines that, not long ago, were associated with hobbyists filming wedding videos or racing through obstacle courses, became a defining instrument of a war that has reshaped how militaries think about killing, surviving, and controlling territory. When Russia launched its full-scale invasion on February 24, 2022, drones were already part of the military toolkit, but they were still largely treated as specialist assets, useful but secondary to tanks, artillery, and aircraft. That perception began changing almost immediately, and by 2023 it had collapsed entirely. The sharp expansion of first-person view strike drones, known as FPV drones, that year marked a turning point. Artillery ammunition was running short on both sides. Traditional precision-guided munitions were expensive, finite, and increasingly difficult to source fast enough for the pace of attritional warfare grinding along hundreds of kilometers of front line. Into that gap came the FPV drone. Cheap, fast to produce, and precise enough to kill. What made these systems so effective wasn't just their price. It was how they slotted into an entirely new battlefield logic, a cycle that now governs life and death across the front. It works like this. A reconnaissance drone goes up first, scanning the terrain, finding the target, a vehicle parked in tree cover, a trench position, a command post, an artillery crew preparing to fire. That target gets identified and its coordinates or live video gets transmitted back to operators within minutes. From there, the information either guides an artillery strike, with the drone hanging overhead to correct the fall of shells in real time, or it hands off directly to an FPV strike drone that flies straight into the target. After the strike, another drone assesses the damage, confirming the kill or flagging the need for a follow-up. Reconnaissance, identification, correction, strike, assessment, the whole cycle, compressed into a timeline that would have seemed extraordinary just a decade ago. This compression matters enormously. When the gap between spotting a target and destroying it shrinks from hours to minutes, the rules of survival change. Concealment stops being an advantage and becomes a requirement. Staying still for too long, clustering vehicles together, leaving equipment in the open. Any of these habits can now result in a strike arriving before anyone has time to react. Soldiers and commanders on both sides have had to internalize a new discipline. Move constantly, disperse, hide, and make decisions faster than the enemy's sensor-to-shooter cycle can close. The drone hasn't replaced the artillery shell or the infantryman, but it has created a persistent surveillance environment in which every element of traditional warfare has to operate differently. The economic logic behind this shift is worth pausing on. A conventional precision-guided munition can cost tens of thousands of dollars, sometimes much more. An FPV drone loaded with an explosive charge can cost a few hundred. When artillery shells are scarce and expensive missiles are being consumed faster than they can be manufactured or imported, the appeal of a cheap, replaceable strike platform becomes obvious. A drone that gets shot down or crashes into its target doesn't represent the loss of a complex, expensive system. It represents the expenditure of a munition that can be replaced by assembling another one, often from commercially available components, in a matter of hours. That replaceability is strategically significant. It means these systems can be used at scale, absorbed as losses without crisis, and iterated rapidly based on what works on the battlefield. Which brings us to the numbers, and the numbers are staggering. Ukraine's National Security and Defense Council reported in late 2025 that its defense industry had built production capacity exceeding 8 million FPV drones per year by 2026. It's worth noting, as with many wartime production figures, that claimed capacity and actual deliveries to the front are different things, and such numbers come from official government sources with their own incentives to project strength. But even accounting for that uncertainty, the scale being described represents a fundamental transformation. This isn't a country buying drones from a contractor and deploying them in limited numbers. This is industrial-scale manufacturing, with supply chains being localized to reduce dependence on foreign components, software being updated based on direct battlefield feedback, and operators, engineers, and commanders working in a fast loop that keeps the technology evolving in near real time. The war has turned drone production into something closer to ammunition production, a continuous, high-volume industrial process rather than a specialized procurement effort. What that means practically is that the drone is no longer a gadget attached to a conventional military. It has become infrastructure, as fundamental to how these forces fight as radios, trucks, or artillery tubes. Both Ukraine and Russia have built dedicated unmanned systems units, reorganized training pipelines, and restructured parts of their industrial bases around the demand that the battlefield generates day after day. The feedback loop between the front and the factory has gotten shorter, more direct, and more consequential. A vulnerability spotted on Monday can produce a design modification by the following week. None of this happened because some visionary military planner decided drones were the future and wrote a doctrine about it. It happened because two militaries locked in brutal attritional warfare found that small, cheap, unmanned aircraft solved real problems of cost, precision, speed, and reconnaissance better than anything else available. The result is a battlefield where the drone is no longer remarkable. It's expected. It's everywhere. And that ubiquity, almost inevitably, produced a response. If small, unmanned aircraft can find you, fix you, and kill you at a fraction of the cost of conventional weapons, then the obvious next priority becomes finding ways to stop them from doing exactly that, which is where the technology arms race that has come to define this conflict really accelerates. That arms race begins with radio waves, because almost every drone on the battlefield depends on them. A standard FPV drone is essentially a radio-controlled aircraft. It receives flight commands from its operator through a radio link, sends live video back through another, and navigates with GPS signals transmitted from satellites overhead. Every one of those radio connections is a potential attack surface, and electronic warfare systems exist specifically to exploit them. Jamming is the most straightforward method. Pump enough radio energy across the right frequencies, and you can overwhelm the control link between operator and drone, cutting the aircraft loose to fall, drift away, or crash. GPS spoofing is more sophisticated. Instead of blocking a signal, you replace it with a false one, feeding the drone's navigation system bad coordinates and sending it off course or into the ground. Even the act of operating a drone creates risk for the human on the other end. Drone operators, launch teams, and command vehicles all emit electromagnetic signals that a capable enemy can detect, locate, and act on. In a battlefield saturated with sensors, being found through your own radio emissions can be as lethal as any incoming round. The result, on both sides of the front line in Ukraine, has been a continuous cycle of adaptation that moves at extraordinary speed. When one frequency gets jammed reliably, operators shift to another. When jamming patterns become predictable, software updates change how the drone hops between frequencies mid-flight. Antennas get modified for directional gain. Flight paths are planned to keep the operator and drone shielded by terrain. New control protocols get developed, tested, broken, and replaced, sometimes within days. This isn't a research and development process happening in a laboratory over years. It's happening in the field, driven by immediate survival pressures, with the results feeding back to engineers and then out to the next batch of operators, in a loop that neither side can afford to pause. Electronic warfare systems have become so dense in some areas of the front that conventional radio-controlled FPV drones become unreliable. Not occasionally jammed, but systematically rendered ineffective over stretches of territory where the EW environment is simply too hostile for radio links to survive. This is the pressure that produced one of the most significant developments of the 2024 and 2025 phases of the war, the fiber-optic FPV drone. The concept is straightforward in principle, even if the execution is demanding. Instead of relying on radio signals for control and video transmission, a fiber-optic drone spools out a thin glass cable as it flies. Commands travel from the operator down that cable to the drone. Video travels back up it. Because no radio transmission is involved, conventional RF jamming has nothing to attack. GPS spoofing doesn't affect the control link. The electromagnetic noise that electronic warfare systems generate becomes largely irrelevant, because the drone isn't listening to radio waves. It's listening to pulses of light traveling through fiber. Russia began scaling this capability in 2024, and reporting from the Kursk area credited fiber-optic drones with meaningful operational impact in fighting there. Ukraine subsequently accelerated its own fiber-optic development, recognizing the same logic applied equally to both sides. Here it is worth being precise about what unjammable actually means in this context, because the word gets used in ways that can mislead. Fiber-optic drones are highly resistant to the radio frequency jamming that neutralizes conventional FPVs. That is a real and significant advantage in environments where EW saturation has made ordinary drones unreliable. But resistant to RF jamming is not the same as invulnerable. The cable itself is a physical object in the world, subject to physical reality. It can snag on trees, fences, rubble, or terrain features. It can break under tension. The drone's maneuverability is constrained by the weight and drag of the fiber it carries, and its range is directly limited by how much cable can be spooled onto the airframe. Fly farther than the cable allows, and the connection simply ends. Manufacturing fiber-optic drones is more complex than assembling standard radio-controlled FPVs. The components are more specialized. Training operators takes more time. The cost per unit is higher. These aren't minor inconveniences. They represent genuine operational constraints that matter when you're trying to produce and deploy weapons at the scale this war demands. So fiber-optic drones solve a specific, critical problem: maintaining a reliable control and video link inside a jammed environment, while introducing a different set of problems. They are not a universal answer. They are a specialized tool that fits a particular tactical situation. And like every tool in this conflict, they will eventually face countermeasures of their own. Kinetic defenses, nets, shotguns, dedicated anti-drone guns don't care whether a drone is radio-controlled or fiber-guided. An operator physically located behind the drone as it unreels its cable is still detectable and targetable by other means. The cable itself might, in time, become a target for directed countermeasures. That points to the broader reality of counter-drone warfare, which is that no single solution works. The battlefield answer to drone threats is not one technology or one tactic. It's a layered combination of many. Electronic warfare forms one layer, jamming control links and video feeds, spoofing navigation, and hunting operators by their emissions. Physical defenses form another. Small arms, heavy machine guns, specialized anti-drone cannons, and missiles each cover different ranges and target profiles. Camouflage and decoys reduce the probability of being found in the first place. Hardening positions and vehicles makes them more survivable when found. And perhaps most fundamentally, rapid and constant movement remains one of the most reliable methods of staying alive, because a target that has moved by the time a strike arrives is a target that survives. None of these countermeasures is sufficient on its own. A unit that relies entirely on EW for drone protection gets destroyed when the enemy adapts frequencies or switches to fiber-optic control. A unit that relies entirely on movement can be tracked and struck in transit if it moves predictably. A unit that relies entirely on camouflage gets found eventually, because persistent aerial surveillance is extraordinarily difficult to evade indefinitely. The answer, on both sides, is to layer these methods, to combine them in ways that force an attacker to solve multiple problems simultaneously, and to keep changing the combination before the enemy can optimize against it. What this arms race has produced, after years of grinding iteration, is something that neither military completely anticipated at the start. A battlefield where the electronic and the physical are inseparable, where the contest between drone and counter-drone is as technically demanding and rapidly evolving as any domain in modern warfare, and where the advantage swings not to whoever has the most impressive technology at a given moment, but to whoever can adapt faster when that technology stops working. Fiber-optic drones are the latest example of that pattern, not its conclusion. The race doesn't stop here. It accelerates. And understanding where it leads requires looking at what the entire drone-saturated battlefield is doing to the fundamental logic of how wars are fought. That question, where the race leads, is not just a question about Ukraine. It's a question about every military on Earth. Because what has been tested in this war is not a regional phenomenon. It is a preview. The most immediate lesson is about visibility. Persistent drone surveillance has fundamentally changed what it costs to concentrate force. In previous wars, massing troops, vehicles, artillery, and logistics was a cornerstone of offensive power. You gathered strength, overwhelmed a point in the line, and exploited the breach. That logic hasn't disappeared, but it now carries a price that didn't exist before. On a battlefield where reconnaissance drones operate continuously, where FPV quadcopters can be airborne within minutes of a target being spotted, and where the sensor-to-shooter timeline has compressed from hours to minutes, concentrating anything large and slow in the open is an invitation to be destroyed, piece by piece, before the mass can be used. Supply convoys, artillery parks, armoured columns staging for an assault, field hospitals, command posts, all of them become targets the moment they can be observed, and observation is now nearly constant. This does not mean tanks are obsolete. It does not mean artillery is finished, or that infantry is irrelevant, or that aircraft have no role. That framing misses the actual lesson. What the drone war has demonstrated is that conventional systems remain necessary, but they now operate inside a persistent unmanned surveillance and strike environment that penalizes exposure and rewards concealment, dispersion, deception, and speed. Tanks that move in small groups, change position frequently, use terrain and camouflage, and operate with dedicated counter-drone protection can still function effectively. Artillery that fires and immediately relocates, that limits its electromagnetic signature, that uses decoys, survives longer than artillery that doesn't. The drone hasn't replaced the tank or the howitzer. It has raised the operational tax on using them carelessly, and militaries that don't pay that tax will suffer for it. The economics of long-range attack have shifted in ways that extend well beyond the front line. Russia's sustained use of Shahed-type one-way attack drones against Ukrainian cities, energy infrastructure, and logistics networks has illustrated a problem for defenders that has no easy resolution. Cheap systems can force expensive responses. A drone that costs a few $1,000s to produce can compel a defender to expend an interceptor worth hundreds of thousands or more. When salvos arrive in large numbers, that arithmetic rapidly becomes unsustainable if the defender relies solely on high-end missiles. The answer, as Ukraine has developed it through necessity, is layered air defense, combining expensive interceptors for the most critical threats with guns, jamming systems, mobile patrol teams, and lower-cost solutions for the rest. But building and sustaining that kind of layered system is itself enormously demanding in resources, training, and coordination. The economic asymmetry favors the attacker who can manufacture cheap systems at scale, and that asymmetry will be a defining feature of future air defense planning for any military that takes it seriously. The reach of small unmanned systems has also extended the concept of strategic strike in ways that blur traditional distinctions between front lines and rear areas. Ukraine's reported Operation Spiderweb on June 1, 2025, which allegedly used small drones to strike Russian airbases, demonstrated that even high-value strategic assets, aircraft, air defense systems, fuel facilities, are no longer safely distant from the threat of inexpensive unmanned systems. The details of that operation remain difficult to independently verify in full, but its reported logic is consistent with a broader pattern. Covertly positioned or long-range unmanned systems can threaten infrastructure and assets that previously required expensive standoff missiles or manned aircraft to reach. That changes how militaries think about base security, dispersal of aircraft, hardening of facilities, and the depth of air defense coverage required. The rear is no longer simply the rear. Artificial intelligence is entering this environment, but carefully and incrementally, not as the sudden arrival of fully autonomous warfare. Current battlefield applications are real and meaningful, but narrower than popular imagination suggests. AI assists with navigation when GPS is degraded or unavailable. It supports target recognition, helping systems distinguish vehicles, personnel, or equipment from background terrain. It improves terminal guidance in the final seconds of an attack run. It assists with obstacle avoidance at low altitude. And it enables limited drone-to-drone coordination, where multiple systems can operate in loose concert without requiring constant individual human input. Analysts studying Russian and Ukrainian AI drone efforts have consistently cautioned that autonomy at scale remains constrained by sensor limitations, weather, degraded communications, training data gaps, and the deeply serious problem of correctly identifying targets under real battlefield conditions. AI is making drones more capable in specific defined tasks. It is not yet producing weapons that think, decide, and act strategically on their own. The trajectory points toward greater autonomy over time, but treating current AI-enabled systems as a fait accompli of machine warfare overstates where the technology actually stands. What is already clear is that military organizations themselves are changing shape around this technology. Ukraine created dedicated unmanned system structures, treating drone operations not as an add-on to conventional units, but as a distinct and integrated capability. Russia adapted its industrial priorities, unit formations, training pipelines, and tactical doctrine around drones and counter-drone operations in ways that are still evolving. The organizational implication for future armed forces is significant. Unmanned systems are moving from a niche aviation capability managed by specialists operating alongside conventional forces, to an integrated force category spanning every domain. Land operations involve ground reconnaissance drones, FPV strike systems, counter-drone teams, and logistics unmanned vehicles. Maritime operations involve surface and underwater unmanned systems capable of surveillance, mining, and direct attack. Air, cyber, and space operations are all being reshaped by the same logic. Persistent, inexpensive, scalable, and rapidly adaptable systems that can be fielded in mass and replaced when lost, rather than preserved at all costs. Navies, armies, and air forces that continue to treat unmanned systems as an afterthought will enter future conflicts with a structural disadvantage that doctrine and training alone cannot overcome. It is also worth acknowledging what these lessons might not tell us. The Russia-Ukraine war is, in important respects, a transitional conflict, fought at the moment when commercial drone technology matured enough to be weaponized at scale. But before directed energy weapons, advanced AI autonomy, quantum-resistant communications, or next-generation active protection systems have been widely fielded. The specific balance between drone offense and drone defense, between cheap attack and expensive interception, between fiber-optic cable and whatever comes next, reflects the technology of this particular window in time. Future advances could shift that balance in ways that are difficult to predict from where we stand now. The lessons being drawn in 2025 and 2026 are real, but they may describe a phase rather than a permanent condition. What they do establish, with clarity, is the direction of travel. Future combat will belong to forces that understand drones not as a single capability, but as an ecosystem. One that encompasses mass production, rapid software iteration, electronic warfare integration, layered air defense, resilient communications that survive jamming, and the organizational agility to absorb new lessons from the field faster than the enemy can exploit old ones. Mass-produced drones without conventional firepower are targets without teeth. Conventional firepower without drone protection and surveillance is blind and exposed. Electronic warfare without layered physical defense is a partial solution. The combination is what matters, and the militaries that invest now in learning how to make that combination work. Not in isolation, in a peacetime exercise, but in the messy, contested, constantly adapting reality of actual conflict, are the ones that will be prepared for what comes next. If you want to understand the future of warfare, you don't need to look at a theoretical scenario. You need to look at what is being learned the hard way right now, and start asking whether your own forces are learning it fast enough.